Am I doing? So today is the 23rd. So the first question is, I'm sorry, Tony, I didn't.
No, we're just proving the formulas given for the hyperbolic functions.
Which formulas are we proving?
Hyperbolic cosine, hyperbolic tangent.
Hyperbolic cosine?
Yes, and hyperbolic tangent.
Yeah, we did that last time.
Yeah, I just was wondering if you wouldn't mind just walking through it.
Of course,
I
no.
watched the video, but I just
Okay,
got lost.
so hyperbolic cosine is that. So I have 1/2 in front. E to the x prime is e to the x. E to negative x prime is e to negative x times the inner function prime. So then this is e to the x plus e to negative x over 2, which happens to be hyperbolic sine.
I treated it like a constant though.
You can't. It
Yeah,
would be 0 then.
Yeah, that's what I was. Alright, thank you.
Sure. And you also need the tangent?
Yes.
Okay. So hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Now I have to use the quotient rule. So the top prime is cosine times the denominator, so I'm going to put it squared, minus the top times the denominator prime, which is sine, so I'm going to put it squared, over hyperbolic cosine squared. But now I have to show what this is. We didn't look into the identities with trig, with hyperbolic functions. So I don't know what this is. So I'm going to take this and square it, take this and square it, and then subtract them. So remember, hyperbolic cosine is this. Hyperbolic sine is the same, just that it has, yes, I messed them up. I just realized. So this is positive here. So this is negative. Sorry about that. So hyperbolic sine is e to the x minus e to negative x. Hyperbolic cosine is e to the x plus e to negative x. Sorry about that. So then I will square this, and then I will square this and subtract them. So I have e to the x plus e to negative x divided by 2, everything squared, and minus e to the x minus e to negative x over 2, everything squared. Because I need to show that this is 1, and you will see this will be 1. So therefore, the answer will be hyperbolic secant squared. So the answer, I'm going to write it up here, hyperbolic secant squared. But I have to show that. Okay? So I will have, from here I take 1/4, and I square this using our contract, the first term squared, plus 2 times the first times the second, which is just 2, plus the second term squared. And then minus, and I square this with minus in front. It will be e to 2x, but then will be plus 2, and then minus e to negative 2x. These two go away. Which two? These two go away. These two go away. So then I have 4 divided by 4, which is 1. So hyperbolic cosine squared minus hyperbolic sine squared is 1. And that's how we get 1 over cosine hyperbolic cosine squared. So then we get secant, hyperbolic secant squared. Is that better?
Yes.
Okay, perfect. Anything else that you worked on, or anything else that you would like to go back to? Again, this is a summary. It's not the type of summary that I have had for you for chapter 2. I will have that for you, but say it again. Okay, but I just want to go over the important information here, right? Quickly in 5 minutes if possible. State the power rule for differentiation. X to the nth prime is good. State the quotient rule for differentiation the way you like it. You don't have to write it the way I like it. So the quotient rule, I like to write this, is 1 prime times 2 minus 1 times 2 prime over 2 squared. don't write mine. If you're using a different one, please feel free to use a different one. State the product rule for differentiation. I like this. 1 times 2 prime in order. 1 prime times 2 plus 1 times 2 prime. Again, disregard mine if you're using a different one. I'm fine. Okay. State the rule for differentiating a sum difference of functions. Hello. No. I was wondering.
Sorry.
We speak English, but not very well. I'm talking about myself, though. State the rule for differentiating sum and difference. Okay, so f plus g prime is f prime plus or minus g prime. State the derivatives of all trig functions. So sine x prime, cosine x prime, tangent x prime, cotangent x prime, secant x prime, and cosecant x prime. So the first one is cosine. The next one is negative sine. The next one is secant squared. The next one is negative cosecant squared. This one is very good, secant tangent. And the next one is negative cosecant cotangent. So these have to be remembered. State L'Hopital's rule and conditions of applicability. All I would like you to remember here is this. Limit of a polynomial over another polynomial when x approaches a is limit as x approaches a from p prime of x over q prime of x only if only 0 over 0 and infinity over infinity. These are the only two possibilities. So when I'm asked to find the limit of a ratio and I have 0 over 0 or infinity over infinity, I am allowed to write limit of p prime over q prime. We're going to come back to this theorem also in chapter 4. Okay, next page. State the chain rule. So here's the chain rule. F comp g of x equals f of g of x. So I want to differentiate this. So I have f prime of g of x times a g prime of x. Excellent. State the power rule combined with the chain rule. So f, a function raised to a power, prime. What will I have for this? Yes, times raised to n minus 1 times, indeed. Very good, excellent. State the derivatives of exponential functions. So e to the x prime and a to the x prime. And also e to u, which is a function, prime, and a to u, which is a function, prime. What do I write for the first one? The first one is always the easiest, e to the x. What do I write for the second one? Times natural log a to the x times natural log a. Similarly for the other two, e to u times u prime, and a to u times u prime, but also times natural log a. Explain the meaning of implicit differentiation. When do I normally use implicit differentiation? When the function is not given to me explicitly. I will implicitly differentiate both sides to get an expression that gives us the derivative, an expression for the derivative. Okay? Explain the meaning of implicit differentiation. I use it when the function is not given to me explicitly. And I will obtain an equation that may have still the function in it, but I don't have the function. And applicability is when I need to determine the rate of change with respect to x, or with respect to t, dy over dx, or dy over dt. Okay. Stated derivatives of inverse trig functions, only 3 of them. So I want sine inverse x prime, cosine inverse x prime, and tangent inverse x prime. The first one. Very good. Square root of 1 minus x squared. Excellent. The second one. The only difference is the minus in front. 1 over the square root of 1 minus x squared. And what about tangent inverse prime?
1 over 1 plus x squared.
Excellent. Stated derivatives of log functions. So we want natural log x. We want natural log of the absolute value of x. We want natural log of a function u of x, all these prime. And we also want log base a of u of x and log base a of u of x prime. The first one. 1 over x. The second one. 1 over x. Very good. Please remember this. Very important. Result I needed in chapter 5. Okay, the next one. 1 over u of x times u prime of x. Excellent. Log base a of x prime. 1 over x times, indeed, 1 over x times natural log a. And the last one, 1 over u of x times natural log a times u prime. Thank you. Times u prime of x. Any questions so far? Any questions so far? Moving on to page 3. Okay, page 3. Explain the meaning of logarithmic differentiation. What will you say in your own words? What is logarithmic differentiation, and when do I need to use it? The main example is when I have to differentiate a function raised to a function. No rule. I only have one possibility, to name this y and do what to both sides? Apply natural log to both sides. So I have to call this y. Y equals f raised to g. I apply natural log to both sides. Natural log y will be g natural log f. That's my only chance. But then I get stuck if I don't know how to find or how to apply what? Implicit differentiation. So just applying log to both sides solved a problem, because I have a function to a function. I have no rule for that. But if I don't remember how to differentiate implicitly, I will not be able to get dy over dx. Perfect. Okay, we have two definitions for number e. So we have limit, so e equals limit, and e equals limit. One of them is 1 plus x, and the other one is 1 plus 1 over x. And this one is 1 over x, and this one is x. But now I have to remember what to put in here. I'm sorry? So, okay, say it again, Ian? Yes, it's x approaches. Right. Remember, both situations have to be 1 to infinity. So that will give you an indication of what to do and where it's going. So this will be to 0, because 1 plus 0 will be 1, 1 to infinity. And this will be 2, right. So easy to remember. The expression is the same, sort of the same, but have in mind that this has to be 1 plus infinity. So x must be approaching 0, because 1 plus 0 will be 1, and this will be the infinity. Now here, x has to approach infinity, because this will be 1 plus 0 now to infinity. Two options of getting e. The derivative of the distant function is, let's say, if I have f of x, its derivative f prime of x will be the same thing with, and I'm going to say that this is the distance, also called displacement. What will this be when I differentiate the distance function? I think we are on page 3 on that handout that I... What will this be? When I differentiate the distance, what do I always get? Very good. So v of x, velocity. Perfect. The derivative of the velocity function, which is v prime of t or x, I'm going to put x, that is, right, acceleration function. Perfect. The marginal cost function is, well, obviously c prime of x. The marginal cost function at a production level of, I just put in a number there, 10,000, is what? C prime of 10,000, of course. Of course. And its meaning is, very important, what is the meaning of C prime of 10,000? It predicts the cost of 10,001. It predicts the cost of 10,001. So is the rate of change of cost with respect to item at the production level of 10,000. But it really predicts the cost of the 10,001 item. So is the rate of change of cost at the production level of 10,000. And I don't have enough room here if you'd like to write predicts. Maybe I can squeeze it in. The cost of the 10,001st item. Steps to follow when solving a related rates problem. What are the steps that I have to go through? Number 1, I read the problem as many times as I need. Number 2, draw a diagram, something like a graph, a diagram, a right triangle maybe, or similar triangles, or a volume of I don't know, cone or sphere, something. I come up with something. Okay. Number 3, write an equation about what I'm asked to find. So number 1, read the problem carefully. Number 2, draw something, whatever it is in the problem. Number 3, come up with an equation that will involve what I'm asked to find. 4, of course, differentiate both sides. Find the derivative of that expression. And 5, and that is the last step, plug in. So number 1, read the problem as many times as I need. Number 2, graph something based on what I'm given. Number 3, write an equation based on what I'm asked to find ultimately. Then differentiate, and then plug in. Solve or plug in the numbers. Linearization of a function near A is L of x, which is f of A plus f prime of A times x minus A. It's a line. The linearization of a function f of x near A. Okay, last page. Of course, since I wrote on that, I have to get it from here. Okay. The linear approximation of a function is, same thing, f of x approximately f of A plus f prime of A times x minus A. The linearization gives us the equation of the line. The linear approximation gives us shows us the same thing basically. You can guess the relationship to evaluate it. The actual difference in a function for a minor difference in the input is called or denoted by the actual or the exact difference in a function for a minor difference in the input. It's called delta y, and the definition is f of x plus delta x minus very good. The differential of a function is denoted how? Yes, but it's y of a function. Good. And what does it equal to? Anyone? This is super important. It comes from this definition. dy over dx equals f prime of x. All you have to do is cross multiply. So remember, these two are interchangeable. But these two also have different meanings now. So just cross multiply. What do I have? dy equals? Of course, f prime of x dx. Excellent. Very good. When using approximations to evaluate a function, we use the following relationship. Super important. F of x plus a little bit is approximately f of x plus a little bit of y. dy is a little bit of y. dx is a little bit of x. So here's how we should remember it easy. We proved all this. So this is not memorization, but we need to think about it. F of x plus a little bit of x is approximately f of x plus a little bit of y. This is dy. This is a little bit of y, and this is a little bit of x. So f of x plus a little bit of x, approximately f of x plus a little bit of y. Okay, list 3 hyperbolic functions and their derivatives. We just talked about them. So hyperbolic sine, e to the x minus e to negative x over 2. Hyperbolic cosine, e to the x plus e to negative x over 2, and hyperbolic tangent e to the x minus e to negative x over e to the x plus e to negative x. So then from here, sine hyperbolic sine prime, we know now is hyperbolic cosine. From here, hyperbolic cosine prime equals hyperbolic sine. And from here, we know that hyperbolic tangent prime equals hyperbolic squared, secant hyperbolic squared, or hyperbolic secant squared. So these are all, this is a condensed summary of what we looked at. So now let's go back to the end of chapter 3, and I'd like to review. If you have questions, if you want to go back to a particular type of problem, we'll start with that. If not, I will pick, and you will pick. I would like to start with problem 89 that caught my eye. 89 on page 266. Any questions for me? Anything that you would like to start with, or can I start with 89 on page 266? Is that okay? Okay. So 89 on 266. Okay. So this problem reads, here it is. A particle moves on a vertical line so that its coordinate at time t is this, for time positive, of course, and 0. Find the velocity and acceleration functions. So that's our first question. So I'm going to copy y. So t greater than or equal to 0, of course. So y equals t cubed minus 12t plus 3. So it moves, a particle moves on a vertical line so that its coordinate at time t is this. So it goes up or down. So that's y, going up and down, height. Okay, so we want to find the velocity, part A, velocity. So I'm going to say v of t. How do I find v of t? What if we just all work for 20 seconds on this, 30 seconds, to find the velocity and acceleration? So t cubed minus 12t plus 3. And I'm going to put my attendance in. I was getting ready to, but I got logged out. Okay, so the velocity is nothing else but y prime, which is 3t squared minus 12. Do we agree with this? Okay, what about the acceleration? Will be y double prime, or it will be v prime of t, same thing, which is 6t. Do we agree so far? Yes? Okay, part B. Let's see what they want in part B. When is the particle moving upward and when it is moving downward? In other words, upward means what sign for y?
Positive.
Positive, and downward?
Negative.
Negative. Very good. So how will I know in which direction the particle is moving? What do I have to do in order to determine that? So first I will set v of t equal to 0 because I need to know when the particle is at rest. I completely agree with that. So then I have 3t squared minus 12 equals 0. Perfect. What will I have to do first? Two keywords are keywords in all math classes. What are they?
Backwards.
Good. Which one is now?
Backwards.
Because it's an equation, I can already divide. I will divide not by a variable ever, but in this case by indeed. So then I have t squared minus 4 equals 0. I know how to solve this equation. T plus 2 and t minus 2. So I have two options. T equals 2 seconds and t equals negative 2 seconds, which cannot be accepted because of this. Good. So now I will study the sign of the velocity function. Remember the velocity now. Now I have to keep the 3 in there. 3 is part of the velocity. 3, t plus 2, t minus 2. So I have t. The domain is definitely 0 to infinity. And I have the 3 doesn't count when it comes to the sign. So t and the velocity.
Why are we still using t minus 2 if we know that it can't be, if we know that it can't equal minus 2?
You're right, it cannot equal minus 2 and it will always be positive. So that will be my assessment right now. Yes. You're correct. So t plus 2 for any t between 0 and infinity will always be positive. Correct. So there is a 2 here and 0. But t minus 2 is a line with a positive slope. It comes from negative values, crosses the x-axis, and goes to positive values. So it's negative and positive. So here's negative and here's positive. So I was asked to identify when is the particle moving up and where is the particle moving down. So what will you say? The particle is moving up or down, whatever you want to start. So particle moving up when t is 0 and 2, in the interval 0, 2. And is moving down, I'm sorry, 2 and infinity. And is moving down when t is in the interval 0, 2. When the velocity is negative, the particle is going down, and when the velocity is positive, it's going up. Any questions? Find the distance that the particle travels in the time interval 0 to 3. So that's our part C. Part C. So for the interval 0 to 3, we're asked to find the total distance. How do I find the total distance? So remember, at time 0, the particle that goes this way for 2 seconds, and then it comes up.
I think you should plug in the distance equation, the time of 2. Right?
Yes. So I will have y of 2 minus y of 0 in absolute value plus y of 3 minus y of 2. And yes, I have to plug them in the function. So let's go here to y equals. Clear if you have anything in there. And let's put in x cubed minus 12x plus 3. X cubed minus 12x plus 3. And I will plug in 0, 2, and 3. 0, 2, and 3. Of course, it went back to going back to the please. Okay. That's not what I meant. Table set. Of course. So second and table. So I want 0, 2, and 3. So S of 2 minus S of 0 will be negative 3 minus 3. The absolute value of negative 13 minus 3 plus y3 would be negative 3 minus negative 13. I have to separate them because they go into different directions. So the distance between time 0 and 2 and the distance between time 3 and 2. So time 0 and 2 and 3 and 2. y2 minus y0, y3 minus y2. So y2 was negative 13 and y0 was negative 3. I'm sorry, it's minus, but 3 plus. So y3, which is negative 3, minus negative 13, which is positive 13. Of course, only this one really needs the absolute value because it's going in the negative direction. The other one will not, but that's okay. It's better to put it on both and not forget. So negative 13 minus 3 is negative 16. The absolute value is 16. 13 minus 6 is 7. The absolute value is 7. So the total distance covered by this particle is 23. Graph the position, velocity, and acceleration functions on 0 to 3. We can. We'll do it in a minute with the graphing calculator. When is the particle speeding up and when is it slowing down? Okay. So if you remember what we did last time with the same type of problem. So this was CDE. So I had t 0, 2, and 3. I had the velocity and the acceleration. So I'm only copying the sign for the velocity. So it's 0 here, negative and positive. And then I will look at the acceleration, which is 6t, which will always be positive because t is greater than or equal to 0. So then I put positive everywhere because it's 6t. And we said the following, that if the velocity is going down, it's a vertical pointing down arrow, a vector, but the acceleration is a vector pointing up, what happens to the particle? The two forces are against each other. So what will happen to the particle? Yes, between 0 and 2, slowing down. But now the two forces, the two vectors are in the same direction. Positive velocity and positive acceleration. They're not working against each other. They are working together. So what do we say between 2 and 3? Speeding up. Oops. Good. And now we can graph all three. So let's do it with the graphing calculator. So I do have the function. I do have now 3x squared minus 12. And I have the acceleration, which is 6x. I'm only interested to see what's happening between 0 and 3. Okay? I don't need the whole thing. I want the viewing window to be between 0 and 3. And the y minimum, I can't really say. I'm just going to say negative 6 for now to positive 6 and see what happens. I see negative 10 and 10 is not working, so this is not good, so I have to go much higher and much lower. So I'm going to say negative 20 to positive 20 with a scale of 5. Maybe that will work. Okay. Okay, it does. Perfect. So I want the graph. Good. So here is the function between 0 and 3. Here is the velocity crossing at 2 because it's 0. And here's the acceleration that is always positive because it's 6x. So when the velocity, which is in blue, when the velocity is negative, so between I'm sorry, I'm looking at the red. That's why. Okay, red. This is the velocity and this is the acceleration. This was the function, the distance function. So this is always positive. So when the velocity between 0 and 2 is negative and the acceleration is positive, the particle is slowing down. When they are both positive, both above the x-axis, between 2 and 3, I see the velocity above the x-axis and the acceleration above the x-axis. They work together, so the particle is speeding up. Any questions on this problem? Okay. Let's look at implicit differentiation. Any particular type that you would like to choose? We're on page 265. Yes, I would like to evaluate that limit 56. That caught my eye. Let's look at 56 first, and then we'll find implicit differentiation. Okay, so we have limit as t approaches 0 from t to the third divided by tangent cubed of 2x. When I'm asked to determine a limit, what is the first thing I have to do? Yes, because I have to identify the type. So when you plug in 0 at the top, what do you get? Good. What do you get when you plug in 0 in the denominator? 0. Ah, I know something that works here. What is it? Yes? Good. L'Hopital's rule. Good. This is the only one time, and only for limits, when I'm allowed to differentiate the top by itself and the bottom by itself. I can never do that. Otherwise, yes, Tony?
I know it has to be like an indeterminate form, or what exactly is that? How do we know if it's an indeterminate form?
You plug in 0, you get 0. You plug in 0, you get 0.
That's all it says. Okay.
You need to do that for any limit.
Yeah.
This is from the very beginning. You always have to plug it in, although we know we are not really allowed to plug it in. But if I don't plug it in, I don't know the case, and I don't know what to do next. So then the top prime would be 3t squared, and the bottom will be yes, tangent squared of 2x times not yet. I still have something till I get to 2.
Secant square.
Secant square of 2x. I'll simplify 3 and 3. Right? So now, yes, I plug in again. I plug in 0. What do I get at the top? Good. Now careful, step by step. The denominator has 2 parts. You can say 3. Well, 2 is 2. I can't do anything to that. So tangent squared of 0. What will this be? I just got tangent cubed to be 0, so how much is tangent squared of 0? Right. What will this equal to? Remember, secant is 1 over cosine. So how much is cosine 0? 1. So how much is secant 0? 1. So I am going to take this number and this number in front of the limit. So I'm going to write 1/2. Because otherwise, I will continue, and you'll still find me here tomorrow morning differentiating this. So this is 1 times 2 is 1/2 in front. So I have limit of t squared over tangent squared to x. Good. Now I have to figure it out what it is. What type is it? Well, I just simplified it, so I already know it's 0 over 0. What should I do next? Have 1/2 in front. I have limit. I forgot to write as t approaches 0. Of what? It's still 0 over 0, so I can continue. The derivative of the top is good. The derivative of the denominator is 2 tangent 2x times secant squared to x times, excellent. This two will go away. How much is this? We already know. 1 times 2 multiplied by 1/2 in front. This is 1/4. Limit as t approaches 0 from t over tangent to x. I can continue before I make sure that I'm still allowed to do the same thing. Am I still allowed to do the same thing to it?
Yes.
Good. So then I have 1/4 in front. Limit t approaches 0. What is the top? Very good. What is the denominator now? Very good. Secant squared 2x times. But how much is secant squared 2x as t approaches 0? I wrote t in, but then oh, I'm sorry. Of course. I had to mess it up. Of course, I meant t. Sorry. Okay, so then this approaches 1. So then the limit is I have a 1/4 here and I have a 1/2 here, so the limit is 1/8. Now, let me show you a different way, which I think is much easier for this particular situation. Limit as t approaches 0, t cubed over tangent cubed of 2t. Okay? Here's another way. Tell me if this is okay. Is t cubed over tangent cubed the same with t over tangent everything cubed? Yes? T cubed is here, tangent cubed is here. That's how we raise a fraction to a power. We raise the top and we raise the bottom. Is this okay? Good. Still, of course, I have 0 over 0. There is no discussion there. So limit t approaches 0. Now I have to break this down into, it's 1 over tangent. So I'm going to have here sine 2t times, because it's sine over cosine, times cosine 2t. So tangent is a ratio. Sine 2t over cosine 2t. And I have to flip it. So I get cosine over sine. What does this approach when t approaches 0? Yeah, exactly. Now keep in mind, this is 2t. What do I need here? Exactly, 2t. So I multiplied the top by 2 and I multiplied the bottom by 2. Can anyone tell us where is this going? Yes, very important limit from chapter 2. What is left inside? A 2 in the denominator, a 1 which is this, and a 1 which is this. So what is left in here? And what half raised to the third power is? But I did not use L'Hopital's rule here. What did I use? I used the result that says this. Limit as the box approaches 0 from either the box over sine of the box or the reversed. Equals how much? If all these are the same and if they go to 0. What is this, the answer? From chapter 2 is 1. Okay. I would like to illustrate a ratio and differentiate it. And I would like to look at a, I don't see here but we can make it up. I would like to make up a problem, an implicit differentiation problem. Can anyone make one up for us? Yes, please. Thomas, go ahead.
Can you move the paper? Shouldn't the tan be squared?
This one? Let's take a look. So I have tangent squared.
Yeah.
I have 2 tangent 2t times secant squared times 2. Good, very good. Would you like to make up a implicit differentiation equation? I mean, equation in which we have to use implicit differentiation. Would you like to look at, say it again,
It
Tony?
looks like number 25 is one, maybe.
Oh, the same page?
Yeah, I think so, yeah.
Okay, let's take a look. You said 25? Excellent. 25 on page 265. They were hiding on the left-hand side. Thank you. Sin xy indeed equals x squared minus y. Perfect. Perfect pick. So we're asked to differentiate this implicitly. No one can solve this equation for y. No human being can. So let's work on this for 30 seconds.